Dear students, welcome to our presentation on the topic subgroups. This is very important chapter. This is unit 2 for semester 3 second year students, degree second year students. Subgroup define చేసే ముందు మనం కాంప్లెక్స్ ని డిఫైన్ చేయాలి. What is a complex? Complex means any non-empty subset of a group G is called a complex. Let G be a group and H is non-empty subset of G, then H is called a complex. Complex means only a subset. Example for a complex. Any non-empty subset. Suppose H is equal to 1. H is equal to 1 set is a complex of a group G is equal to 1 comma minus 1. H is equal to minus 1. H is equal to minus 1 is a complex of a group G is equal to 1 comma minus 1. It is a finite group with respect to multiplication. Identity element is 1. These are the examples. The set of even integers is a complex of the set of integers. So complex definition and examples one example. So subgroup define cheyali. Very important. The complex subgroup eppudu avutundi. Definition of a subgroup. Define a subgroup and give an example and examination lo istaru. So subgroup define chese mundu manam group gurinchi cheppali. So let G be a group and H is a complex of G. H is said to be a subgroup of G if H is itself a group with respect to the same operations of G. G group. H is a complex. H complex subgroup అవ్వాలి అంటే Gకి Gలో ఏదైతే ఆపరేషన్ ఉందో అదే ఆపరేషన్తో H కూడా గ్రూప్ అవ్వాలి. Very important. So G is a group with respect to multiplication. Then H is also a group with respect to multiplication. G is a group with respect to addition, then H is also a group with respect to addition. So H is itself a group with respect to same operations of a group G. So examples for a subgroup. We know that N is subset of Z, Z is subset of Q, Q is subset of R, and R is subset of C. So natural numbers, integers, rational numbers, real numbers, and complex numbers. We know that Z plus is a group. Z is a group with respect to addition. So N is not a group. N plus is not a group. N plus is not a group. Since N is equal to set of 1, 2, 3 and so on. So this set N does not contain 0 element. Additive identity E is equal to 0 does not exist in N. Then N plus is not a group. So Z plus is a group and Q plus, the set of rational numbers, is a group with respect to addition, and Z is subset of Q. Z is subset of Q. Z is subset of Q. This means Z is a subgroup of Q. Similarly, R plus is a subgroup. R plus is a subgroup of C plus. R plus is a group and C plus is a group. So R is subset of C. This gives R plus is a subgroup of C plus. These are the examples for additive group. Next, multiplication. Consider a set H is equal to 1 comma minus 1. Minus 1 is a subgroup of a group G is equal to 1 minus 1 I minus I. The fourth roots of unity where I square equal to minus 1. I square equal to minus 1. So it is a subgroup. H is equal to 1. Consider a set H is equal to 1 is a subgroup of a multiplicative group G is 1 comma minus 1. It is a subgroup. These are all subgroups. Examples for subgroups. Subgroup means subgroup is itself a group with respect to same operations of a group G. Multiplication or product of complexes. Let G be a group and H and K are two complexes of a group G. The product of HK is denoted by HK and is defined as the set is HK such that H belongs to H, K belongs to K. K belongs to K. That is, H belongs to H, K belongs to K. This gives HK belongs to HK. This is the product of two complexes, HK. The product of HK is also a complex of G. Multiplication of complexes is also associative. HKL are three complexes of a group G, then H into KL is equal to HK into L. This is the product of two complexes definition. The inverse of a complex, very, very important. Inverse of a complex. Let H be a complex of a group G, then the inverse of H is denoted by H inverse and is defined as H inverse such that H belongs to H. This is the definition of inverse of the complex. That is, H belongs to H gives H inverse belongs to H inverse. The inverse of the complex. Suppose H is equal to -1 is a complex of a group G is equal to 1 comma -1. It is a finite group. H is a subset of G. Clearly H is a complex. So it is denoted, inverse of H is denoted by H inverse. This is equal to -1 whole inverse. -1 whole inverse is equal to, this is -1. -1 equal to H. Here inverse of -1 is -1. -1 into -1 equal to 1. That is, A dot B is equal to E gives B is equal to A inverse. B is the inverse element of A. H inverse, inverse of the complex. Definition of improper or trivial subgroups. Let G be a group and H is a subgroup of G, where E is the identity element in a group G. Consider a set H is equal to set of E. Set contain only one element. That element is identity element. Clearly H is subset of G. We know that every set is itself a subset. Consider H is equal to G. These two subgroups, H is equal to E and H is equal to G, are known as improper subgroups. Improper subgroups of a group G. All other subgroups, if exists, are known as proper subgroups. H is equal to E and H is equal to G ఈ రెండు కాకుండా వేరే సబ్గ్రూప్ ఏదైనా ఎగ్జిస్ట్ అయితే దాన్ని ప్రాపర్ సబ్గ్రూప్ అని అంటారు. ఒక ఎగ్జాంపుల్ ద్వారా చెక్ చేద్దాం. కన్సిడర్ ఏ సెట్ G is equal to 1 omega omega square cube roots of unity where omega cube is 1. It is a finite abelian group with respect to multiplication. The subsets of G are H is equal to 1 and H is equal to 1 omega omega square. Only two subsets, 1 omega omega square. Clearly, H is equal to 1 and H is equal to G are two subgroups of a group G. Here consider H1. It is denoted by H1 and H2. These are two subgroups. These subgroups are known as improper subgroups. The cube roots of unity contains only two subgroups. These are improper subgroups. Consider another example. Fourth roots of unity. Consider a set G is equal to 1 minus 1 I minus I, where I square equal to minus 1. The cube roots of unity, it is a finite abelian group with respect to multiplication. Consider H1 is equal to 1, where E is the 1 multiplicative identity, and H2 is equal to 1 comma minus 1, and H3 is equal to 1 minus 1 I minus I, that is G. Here H is equal to 1, H is equal to 1, H is equal to H3 equal to G. These two are improper subgroups. Improper subgroups, and H2 is a proper subgroup. The fourth roots of unity contains two improper subgroups and one proper subgroup. These are the examples for proper and improper. H is equal to E and H is equal to G, remember, these two are improper subgroups of a group G with respect to multiplication. All other subgroups, if exists other than H is equal to E and H is equal to G, are known as proper subgroups. Theorem: if H is a subgroup of a group G, then prove that HH is equal to H. H subgroup అయితే HH is equal to H అని చెప్పాలి. ఇప్పుడు A is equal to B అని ప్రూవ్ చేయాలి అంటే మనం లోయర్ క్లాస్లో నేర్చుకున్నాం. If and only if A is subset of B and B is subset of A. A Bకి సబ్సెట్ అవ్వాలి, Bకి Aకి సబ్సెట్ అయితే మనం A is equal to B అని రాస్తాం. మనం ప్రాక్టికల్గా ప్రూవ్ చేసేటప్పుడు A is subset of B అని ప్రూవ్ చేయాలి. A is subset of B means all the elements in A are the elements in B. ఏలో ఉండే అన్ని మూలకాలు Bలో ఉండాలి. ఏలో ఉండే అన్ని మూలకాలు Bలో ఉండాలి అంటే మనం ప్రూవ్ చేసేటప్పుడు ఏలో ఒక ఎలిమెంట్ తీసుకోండి. లెట్ X బిలాంగ్స్ టు A అని తీసుకొని అదే X అనే ఎలిమెంట్ Bలో ఉందని చెప్పగలిగితే X belongs to A gives X belongs to B, then we write A is subset of B. ఏలో ఉండే మూలకాలన్నీ Bలో ఉన్నాయని ప్రాక్టికల్గా ప్రూవ్ చేయాలి. ఇక్కడ ఈ థియరంలో మనం HH is equal to H అని చెప్పాలి. We prove that HH is equal to H. HH is equal to H means HH is subset of H and H is subset of HH అని మనం ప్రూవ్ చేయగలిగితే మన HH is equal to H అవుతుంది. ఇక్కడ మల్టిప్లికేషన్ ఆఫ్ కాంప్లెక్సెస్ చూడండి. HK is equal to set of HK. HK is equal to set of small elements HK such that H belongs to H and K belongs to K. This is the definition, multiplication of complexes. So here HH, the product of two subgroups, HH is equal to H1, H2 such that H1 belongs to H, H2 belongs to H. ఇక్కడ మనము HH is subset of H అని చెప్పాలి. ఫస్ట్ పార్ట్లో HH is subset of H అంటే ఏమని చెప్పాలి? HHలో ఉండే ఎలిమెంట్ ఒకటి తీసుకుని అదే ఎలిమెంట్ Hలో ఉందని చెప్పగలిగితే మనకు HH is subset of. ఇక్కడ లెట్ X belongs to HH అని తీసుకుంటాం. X belongs to HH అని తీసుకుంటే XHH definition ప్రకారం ఏంటి? HH is equal to H1, H2 such that H1 belongs to H, H2 belongs to H. That gives X is equal to H1, H2. X is H1, H2, where H1 belongs to H, H2 belongs to H. H1 belongs to H, H2 belongs to H. Since H is a subgroup, H is a subgroup means H is itself a group with respect to same operations of a group. So H subgroup means H is a group by closure property. H1 belongs to H, H2 belongs to H. This gives H1, H2 also belongs to H, closure property. Since H is a subgroup, H satisfies all conditions of group closure, associative, identity and inverse property. Here H1, H2 is X. This gives X belongs to H. యాక్చువల్గా ఎక్స్ అనే ఎలిమెంట్ మనం ఎక్కడ తీసుకున్నాం? హెచ్లో తీసుకున్నాం. అదే ఎక్స్ అనే ఎలిమెంట్ హెచ్లో ఉంచండి. దేర్ఫోర్ ఎక్స్ బిలాంగ్స్ టు హెచ్ గివ్స్ ఎక్స్ బిలాంగ్స్ టు హెచ్. దిస్ మీన్స్ హెచ్ ఈజ్ సబ్సెట్ ఆఫ్ హెచ్. దిస్ ఈజ్ ఈక్వేషన్ 1. హెచ్ ఈజ్ సబ్సెట్ ఆఫ్ హెచ్ అని చెప్పాలి. అదేవిధంగా హెచ్ ఈజ్ సబ్సెట్ ఆఫ్ హెచ్ అని చెప్పగలిగితే మన హెచ్ ఈజ్ ఈక్వల్ టు హెచ్ అవుతుంది. ఈక్వేషన్ 1 అన్న. నెక్స్ట్ రెండో పార్ట్ మనం హెచ్ ఈజ్ సబ్సెట్ ఆఫ్ హెచ్ అని చెప్పాలి. హెచ్ ఈజ్ సబ్సెట్ ఆఫ్ హెచ్. ఇక్కడ మనం హెచ్లోకి ఎలిమెంట్ తీసుకుని అదే ఎలిమెంట్ హెచ్లో ఉందని చెప్పాలి. లెట్ వై బిలాంగ్స్ టు హెచ్ అని తీసుకున్నాం. ఒక ఎలిమెంట్ తీసుకున్నాం. సిన్స్ జీ ఈజ్ ఏ గ్రూప్, ఈ ఈజ్ ది ఐడెంటిటీ ఎలిమెంట్ ఇన్ జీ. గ్రూప్ లో సబ్ గ్రూప్ లో ఐడెంటిటీ ఎలిమెంట్ ఒకటే ఉంటుంది కాబట్టి ఈ బిలాంగ్స్ టు జీ, వేర్ ఈ బిలాంగ్స్ టు హెచ్. వై బిలాంగ్స్ టు హెచ్, ఈ బిలాంగ్స్ టు, సిన్స్ ఈ బిలాంగ్స్ టు హెచ్, ఈ ఈజ్ ది ఐడెంటిటీ. సో by multiplication of complexes, y belongs to h, e belongs to h. This gives ye belongs to h. Y belongs to h. by product of complexes. Y belongs to. Since E is the identity element, since A belongs to H, A belongs to G, gives AE is equal to EA is equal to A for all A belongs to G by identity property. YE, Y belongs to H means since Y belongs to H, Y belongs to H gives Y, H is subset of G, so Y belongs to G. Here YE is equal to YE is equal to EY is equal to Y for Y belongs to H. So YE is equal to Y. This gives Y belongs to H. యాక్చువల్గా Y అనే ఎలిమెంట్ హెచ్లో తీసుకున్నాం. అదే Y అనే ఎలిమెంట్ హెచ్లో ఉంది కాబట్టి therefore Y belongs to H gives Y belongs to HH. This gives H is subset of HH. H is subset of HH. Equation 2. ఇక్కడ చూడండి ఈక్వేషన్ 1లో HH is subset of H and H is subset of HH. This gives from 1 and 2 we get HH is subset of H and H is subset of HH. This gives HH equal to H. HH equal to H. So A is subset of B and B is subset of A gives A is equal to B. So H is a subgroup. We write HH is equal to H. Hence proof. Theorem. If H is a subgroup of a group G, then prove that H inverse equal to H. H subgroup అయితే H inverse is equal to H అని చెప్పాలి. H inverse is equal to H అంటే A is subset of B and B is subset of A gives A is equal to B. A B కి సబ్సెట్ B A కి సబ్సెట్ అయితే A is equal to B అని రాస్తాం కాబట్టి మనం H inverse equal to H అని ప్రూవ్ చేయాలి. H inverse is H gives H inverse is subset of H and H is subset of H inverse అని ప్రూవ్ చేయగలిగితే H inverse is equal to H అని రాస్తాం. మనకి A is subset of B అని ప్రూవ్ చేయాలంటే ఆల్రెడీ లాస్ట్ థియరంలో చేసాం. A is subset of B. ఏలో ఒక ఎలిమెంట్ తీసుకుని అదే ఎలిమెంట్ బిలో ఉందని చెప్పగలిగితే మనకి ఏ సబ్సెట్ ఆఫ్ బి అవుతుంది. ఆల్ ది ఎలిమెంట్స్ ఆఫ్ ఏ ఆర్ ది ఎలిమెంట్స్ ఆఫ్ బి. ఇక్కడ మనకి హెచ్ ఇన్వర్స్ లో ఉండే ఎలిమెంట్ ఒకటి తీసుకుని అదే ఎలిమెంట్ మనం హెచ్ లో ఉందని చెప్పగలిగితే ఆటోమేటిక్ గా మనకి హెచ్ ఇన్వర్స్ ఇస్ సబ్సెట్ ఆఫ్ హెచ్ అవుతుంది. ఇక్కడ బై ఇన్వర్స్ ఆఫ్ ది కాంప్లెక్స్ డెఫినేషన్ ప్రకారం హెచ్ ఇన్వర్స్ ఇస్ ఈక్వల్ టు హెచ్ ఇన్వర్స్ సచ్ దట్ హెచ్ బిలాంగ్స్ టు హెచ్. Inverse of the complex, that is H belongs to H, H inverse belongs to H inverse, that is H belongs to H gives H inverse belongs to H inverse. This is the inverse of the complex definition. ఇక్కడ మనం H inverse equal to H అంటే H inverse is subset of H and H is subset of H inverse అని చెప్పాలి. ఫస్ట్ ఇక్కడ ఒక ఎలిమెంట్ తీసుకున్నాం. H inverse లో ఒక ఎలిమెంట్ తీసుకొని అదే ఎలిమెంట్ H లో ఉందని చెప్పగలగాలి. Let X belongs to H inverse of this. X belongs to H inverse and by definition of the inverse of the complex, H inverse is H inverse. That is X is equal to H inverse where H belongs to H. X is H inverse. Since H is a subgroup, by definition H is itself a group by satisfying inverse property. Since H belongs to H, thus gives H inverse also belongs to H by inverse property. Every element having multiplicative inverse. Since H is a group with respect to multiplication, H inverse here, H inverse is X. This gives X belongs to H. Actually, X ఎక్కడ ఎలిమెంట్ H inverse లో తీసుకున్నాం. అదే X H లో చూడండి. Therefore, X belongs to H inverse. This gives X belongs to H. X inverse లో ఎలిమెంట్ H లో ఉంది కాబట్టి then we write H inverse is subset of H. This is equation 1. First part. Next second part లో H inverse H is subset of H inverse అని చెప్పాలి. H is subset of H inverse. చూడండి H is subset. ఇక్కడ ఒక ఎలిమెంట్ తీసుకున్నాం. హెచ్లో వై అనే ఎలిమెంట్ తీసుకుని అదే ఎలిమెంట్ హెచ్ ఇన్వర్స్లో ఉందని చెప్పాలి. లెట్ y belongs to h. Y belongs to h since h is a subgroup of a group G, so h is itself a group. By inverse property, y inverse belongs to h. Inverse property. By inverse of the complex definition, y inverse whole inverse is also belongs to h inverse. Since h belongs to h, gives h inverse also belongs to h inverse by definition of the inverse of the complex. A inverse whole inverse, since A inverse whole inverse is A, this gives Y inverse whole inverse is Y. This is Y belongs to H inverse. Actually Y అనే ఎలిమెంట్ ఎక్కడ తీసుకున్నాం, హెచ్లో తీసుకున్నాం. అదే Y అనే ఎలిమెంట్ హెచ్ ఇన్వర్స్లో ఉంది కాబట్టి మనం ఎవరు రాయొచ్చు, therefore Y belongs to H gives Y belongs to H inverse. This gives H is subset of H inverse. This is equation 2. So equation 1, H inverse is subset of H and H is subset of H inverse is equation 2. From 1 and 2 we get H inverse is subset of H and H is subset of H inverse. This gives H inverse equal to H. H inverse equal to H. H subgroup అయితే H inverse is equal to H in prove చేసాం. Hence proved. Hence proved. Converse of the above theorem need not be true. Converse of the above theorem means H subgroup అయితే H is a subgroup. We proved that H inverse equal to H అని prove చేసాం. ఇక్కడ H is equal to H inverse అయినంత మాత్రం అది సబ్ గ్రూప్ కావాల్సిన అవసరం లేదు అనేది కాన్వర్స్. ఇప్పుడు మనం గ్రూప్ కన్సిడర్ చేద్దాం. Consider a group H is equal, G is equal to 1, -1. It is a finite abelian group with respect to multiplication where the identity element is 1. And consider a set H is equal to 1. H is equal to 1. This gives H inverse. By inverse of the complex definition, H inverse is 1 inverse. 1 inverse. Inverse of 1 is 1. Identity element having self inverse. Since 1 inverse equal to 1. 1 into 1 is 1. E inverse is E. So H is equal to is 1. H inverse equal to H. Here H inverse equal to H. H inverse equal to H and H is also a subgroup. H is a subgroup of G. Next, example 2. Consider a set H is equal to -1. Single element -1. So H inverse is equal to -1 whole inverse. -1 whole inverse is equal to inverse of -1 is -1. Since -1 into -1 is equal to 1. So A dot B is equal to E gives B is equal to A inverse. Inverse dip. H inverse equal to H -1. Here H inverse equal to H, but H is not a subgroup. H is equal to set of -1, but H does not contain an identity element. E is equal to 1. So with respect to multiplication, identity element E is equal to 1 must be exists in a subgroup. So H is equal to -1 is only complex but not a subgroup. So H is equal to H in both examples. H is equal to H inverse we get, but in case 1, H is equal to 1 is a subgroup, but H is equal to -1 is not a subgroup. So converse of the above theorem need not be true. H is equal to H inverse అయినంత మాత్రాన H సబ్ గ్రూప్ కావాల్సిన అవసరం లేదు అనే దానికి మనం 2 ఎగ్జాంపుల్ ద్వారా చెక్ చేసుకుందాం.